Good morning and welcome to AIST's Decarbonization Webinar Series. My name is Charlie Bender and I'm a staff engineer here at AIST, and I'm joined with moderators and presenters today for a presentation on blast furnace decarbonization. We thank you all for joining in person, and we have a few AIST webinar guidelines to go through. Your attendee audio has been disabled, and all questions to the presenter should be submitted through our Q&A feature. Our host and moderator will determine which questions are presented to the presenter, and this session is being recorded and will be available on demand replay on AIST's website. Photos or recording of this presentation is prohibited, and technical support is available at the following training@aist.org email. AIST has two important guidelines: antitrust and anti-harassment policies. We expect everyone attending to follow both. Again, questions are available to the presenters. Some will be answered live. If everyone is not answered at the end of the webinar, there is a contact method for discussion later with the presenters. The AIST Decarbonization Series has a history of long string of webinars. A few are shown on the screen now. And I'd like to take a moment to introduce our moderators, both Joe Mori and Manu Rade. Joe is the owner of Mori Industrial Consulting, who provides primary steelmaking advisory services, specializing in assisting companies reduce their carbon footprint at the best overall cost and value. Joe's active client list includes Limelight Steel and Orzinga Cement, two companies poised to make an impact in this effort. Joe has over 28 years of international operational and technical steelmaking experience with U.S. Steel. Joe is a current member of the AIST Board of Directors and is the Vice Chair for the AIST Decarbonization Subcommittee. Our second moderator is Manu Rade. Manu is the General Manager of Raw Material Strategy and Supply for Steel Dynamics Flat Roll Group. Manu joined Steel Dynamics after more than 30 years of experience with ArcelorMittal and its predecessor companies. He began his career in Inland Steel's R&D division in East Chicago, Indiana, where he worked on raw materials, ironmaking, and steelmaking. He advanced through technical, operational, managerial, and leadership roles, serving as Vice President of ArcelorMittal and General Manager of the Indiana Harbor Works, and then the Burns Harbor Works. In 2013, he transitioned to the mini mill sector, successfully leading Steel Dynamics' modern flat-rolled electric furnace mini mill in Columbus, Mississippi, as its GP and GM for 7 years before taking on his current role in 2021. Manu is a distinguished member and fellow of AIST, and he is also an active member of AIST's Decarbonization Subcommittee. Manu earned his master's degree in material science and mineral engineering from the University of California, Berkeley, and a bachelor's degree in metallurgical engineering from the Indian Institute of Technology, Mumbai. Our moderators will now introduce our presenters.
While Charlie's bringing up the slides, I'll just go ahead and start giving our little discussion here. We're here talking about blast furnaces and decarbonization, which is kind of a strange mixture. Why are we talking about trying to decarbonize the blast furnace route? The Paris Climate Accord came to pass, and there's a lot of signatories on this accord, and we all promised that we're going to reduce our carbon footprint as a whole world, and steelmaking is no small part of that. As you can see here, since the signing of the Paris Climate Accord, we've actually increased our as far as steel goes, our carbon footprint by 5% actually, from 2007 to 2023, and there's no sign that it's slowing down either. So it seems that there's a strong iron a blast furnace footprint for iron making. Over 70% of the world's steel comes from traditional blast furnace routes and blast furnace capacities that continue to come online. Can you go to the next slide, please? As you can see here, in North America and Europe, there's blast furnaces that are shutting down there, and in parts of Asia, blast furnaces continue to come online, and it just continues to balance out at around 70%. That figure has been stable for the past 10 to 15 years. Go to our next slide. So today, we're going to talk about the second part of our series where we talked about this pathway before. Now we're going to be focused on the boiler house, blast furnace, and steel making area on what exactly we can do to reduce our carbon footprint, which is the biggest lion's share of the carbon emissions. And so now I'd like to turn it over to Madhu to introduce the first of our presenters.
Thank you, Joe. You summarized very succinctly the current dilemma that although we are looking at new processes that are going to be zero net carbon, the blast furnace process continues to predominate, and we need to do something about it right now rather than waiting for another 20, 30 years. So the goal of our webinar today is to learn about what are the currently available practical and pragmatic technologies that can achieve significant reductions in carbon emissions right now from existing blast furnaces and existing BOF facilities well before the cutting edge technologies that are on the drawing board can be commercialized. You are in for a treat today. Our first presentation is by Renaud van Laar, also affectionately known as RJ. RJ is from the Netherlands. He has an MSc degree in applied physics from Delft University of Technology. He's been employed within the ironmaking, plant engineering, and technology departments of Hoevens Technical Service and Danielle Chorus in the Netherlands since 1996. More recently, he's been assigned to the blast furnace and BOF decarbonization technology development with Danielle Chorus. Danielle Chorus is part of Danielle Group, which comprises plant engineering and steelmaking divisions. So Renaud would be talking about realistic and effective technologies to reduce the blast furnace and BOF CO2 emissions. So RJ?
All right. Ladies and gentlemen, thank you for attending this webinar. And I have the honors to share the first presentation today, Realistic and Effective Technologies to Reduce Blast Furnace and Basic Oxygen Furnace CO2 Emissions. And within this first presentation, I will actually cover 5 different sections. It's my pleasure to first start with a general introduction into the remainder of this presentation. I think we're all in agreement that any CO2 emissions requirements reductions has a significant impact on our industry, mainly due to their challenges. But at the same time, the silver lining, it also drives innovation and development of new technologies. Nonetheless, I would like to summarize some of the challenges that are being faced by our industry for the decarbonization, such as limited availability of green electricity, constraints in the availability of high-grade iron ores and scrap, limited availability, if any at all, on hydrogen infrastructure, We cannot ignore the risk and the challenge of scaling up any new technologies. This simply takes time in our industry. CapEx and OpEx economics, and also the green steel premium. And last but not least, the moderators already explained, we are running out of time. We can wait for new emerging net zero technologies, but realistically, this will take another few years. And actually, within our organization, we are convinced that a significant part of steel making for the coming decades will comprise basic oxygen furnaces and also blast furnaces, which is why we are determined to assist the industry in decarbonization of blast furnace and basic oxygen furnace. And for this reason, we started an internal assessment a little while ago to assess actually the impact and the effect of different technologies that could be used for decarbonization of blast furnace iron making and basic oxygen furnace steel making. And for this purpose, we set up a rather comprehensive spreadsheet model, which includes all of the main facilities of a typical integrated iron and steel making plant, such as sinter making, pellet making, coke making. Also iron making, either by blast furnace, but also potential new direct reduction plants on site or remote. Steel making by means of basic oxygen furnaces, casting. And the spreadsheet model also includes oxygen and steam, and last but not least, electricity and hydrogen. And any usage of hydrogen does matter because we have been assuming that any hydrogen would realistically be made by contemporary electrolyzers which are connected to the grid. And the electricity grid carbon intensity these days is generally anywhere 300, 400, 500, 600 grams of CO2 to produce 1 kilowatt hour. So we cannot ignore those emissions as there's simply not enough green electricity as we speak to service the steelmaking industry. Maybe on the longer run using nuclear energy or other sustainable energies. And by realistic technologies, we actually mean implementation within the next 5 years. So this would not take 10 years, 15 years, 20 years, but within the coming years, the realistic technologies could be implemented in our industry. And actually within our comprehensive spreadsheet model, we are using any and all of the off gases. We are assuming top gas recovery turbines are included. We are assuming that any steelmaking gases are used to produce steam, etc., and any other excess gases would actually be used to produce electricity that could be exported after some of this electricity is used within the plant. And we have actually been looking into a typical large blast furnace with a coke rate of 340. There's a little conservative number and a coal injection rate of 180. And I would say the other key KPIs are rather reasonable. And within the spreadsheet model, we've actually been using the detailed results of our thermodynamic blast furnace steady state heat and mass balance model. But we've also been assuming, I would say, realistic constraints as these are commonly accepted in our industry on minimum coke rate, minimum top gas temperature, and draft for using PCI or natural gas. And if we would then add up all of the emissions of sinter making, pellet making, coke making, etc., then the total emissions of this reference plant would add up to a number of around 2067. And we need to knock down this number. And within the remainder of the presentation, we will actually take you along on our journey by analyzing 3 different technologies to reduce those crude steelmaking emissions to less than 1,600. And by the end, I will actually also share a forecast because that number could be even more reduced in another few years. How could the number of 2,067 kilos of CO2 be reduced, I would say, right away? Well, there's 2 methods to reduce these emissions right away. That is first to implement best available technologies. And 3 such examples are summarized on this slide, which is a modern charging unit to reduce the coke rate by more optimum burden distribution and maximize the gas utilization. The second is to adopt modern hot blast stoves with a hot blast temperature of 1200 degrees centigrade instead of the more conservative 1100 degrees centigrade. And last but not least, by implementing, I would say, modern state-of-the-art automation level 2 systems, including, as an example, heat flux monitoring to reduce the heat losses by gas flow along the reactor. Second, right away, the industry can further optimize efficiency and yield of blast furnace iron making and basic oxygen furnace steel making. And some 5 examples that we came across into some steel making companies are summarized on this slide. For example, minimizing the burden moisture and roll fluxes, maximize the yield and recycling of fines and reverts, maximizing hot blast temperature also by using energy-saving tweer stocks and tweers. And when we look into basic oxygen furnace, we have come to realize that many steelmaking companies could actually optimize their logistics to minimize the heat and the yield losses, and also to maximize the energy efficiency, for example, by usage of ladle covers. And if the best available technologies and some efficiency and yield improvements are being factored in, then emissions will be reduced already by some 5%. As a result of improving the gas utilization, reducing heat loss in blast furnace, increasing the hot blast temperature. This will reduce the coke rate whilst retaining the PCI rate. And by reducing the coke rate, overall carbon emissions will be reduced to a level of approximately 1,981 kilos of CO2 for 1 ton of crude steel. And this reference steelmaking plant, a modern reference steelmaking plant, is actually a net exporter of electricity of around 134 kilowatt hours for each ton of crude steel. By nature of combustion of any excess blast furnace gas and coke oven gas, and use that heat to generate export electricity. Now, let us look into one potential technology to reduce the CO2 emissions, which is usage of gas injection. We have been analyzing 3 different types of gas injection. The first, already practiced in the United States, also in Russia and 1 or 2 other countries. We could look into usage of natural gas, and we've been assuming this is constrained by maximum amount of approximately 100 kilos per ton of hot metal, and it would actually rule out usage of PCI. Second, we've been assessing the impact of using coke oven gas instead at, I would say, a moderate rate of 40 kilos for 1 ton of hot metal, and another 180 kilos of PCI. You may wonder why 40? Well, we have come to realize that the availability of coke oven gas on its own is limited by the coke making plant. And some coke making plants, they may produce more coke oven gas, others may produce a little less, but we believe that a moderate average number for our industry would allow usage of approximately 40 kilos of coke oven gas for each ton of hot metal, as we also need to use minor amounts of coke oven gas for enrichment in hot blast stoves, but also for heating in the reheat furnaces. Third, we've been looking into usage of hydrogen, and we have been assuming a moderate, reasonable rate is some 20 kilos of hydrogen for 1 ton of hot metal. 2 industrial plants in our industry have already demonstrated usage of hydrogen in excess of 10 kilos on industrial facilities. And experimental blast furnaces have already demonstrated capability to inject much higher levels, even beyond 40 kilos. But there are some setbacks of doing this on the heat balance. So we've been assuming a moderate amount of 20 kilos. Let us first look into the KPIs of the blast furnace when comparing natural gas, coke oven gas, and hydrogen. And as you can see, the coke rate for injection of natural gas is relatively high because we have nullified coal injection rate in order to allow maximum usage of gas. The coke oven gas coke rate and hydrogen coke rate are less than our reference blast furnace, which means that CO2 emission reductions will be accomplished. And for your information, the reference blast furnace plant had a coke rate of 313 kilos. More interestingly, let's look into the impact to the electricity balance. The potential export of electricity will double when injecting natural gas because more blast furnace gas at a higher calorific value will be produced. The export of electricity will be reduced to only 32 kilowatts when injecting coke oven gas because there would be no more coke oven gas for combustion in power plant to produce electricity. And far worse is actually the electricity balance when injecting hydrogen. Then we would need to factor in the usage of more than 800 kilowatt hours to produce 1 ton of crude steel by means of injecting of 20 kilos of hydrogen. Nonetheless, the three scenarios reflect a reduction in CO2 emissions, but this impact for injection of natural gas is rather limited, which is obvious because natural gas, the main component is actually carbon. More significant savings could be realized by injecting coke oven gas, and the most emissions reduction could be achieved by injecting hydrogen. We've also actually been comparing those numbers with papers and reports by other people in our industry, and we believe that they're reasonably consistent. So if you would look into this, then injection of natural gas has a very limited impact in reducing CO2 emissions. There's a more significant impact when injecting coke oven gas, and the most significant impact for scope 1 emissions would be to inject hydrogen. But in a realistic assessment, we can actually not ignore the source of electricity. And here scope 2 emissions come into play. As I had explained, there's not many countries in our industry that have low carbon grid intensity. Only France and Sweden produce electricity with a grid intensity of less than 100. Most other countries in Europe, anywhere between 300 and 400. Most countries in Asia produce electricity with a grid intensity of more than 500 grams of CO2 for 1 kilowatt hour. That means that we need to factor in a penalty when using electricity for the electrolyzers to generate hydrogen, unless any other emerging technologies will arise to produce hydrogen without the need for such electricity. And what happens next, if you look into a comparison of these graphs, then despite the fact that hydrogen injection is the most effective for scope 1 emissions, it actually is worse than current emissions if the grid intensity would be higher than 120 grams CO2 for 1 kilowatt hour. So injection of hydrogen is only meaningful if there would be sort of large amounts of green electricity, and not just green electricity, it must also be affordable green electricity. Instead, coke oven gas injection in this scenario will always be more attractive than continuing existing steelmaking operations, and natural gas injection is also reasonable. Let's look into another group of technologies which includes charging of metallics in the blast furnace. And I deliberately refer to metallics. What are metallics? Metallics could be DRI, HBI, even scrap. Metallics could also include briquettes if they are mainly made up by iron reverts. And we've been looking into different scenarios of charging metallics in the blast furnace. And within this presentation, we will focus particularly on charging DRI. And actually, the examples that I will be sharing in the next few slides assume 30% of the burden comprises DRI. And there's a good reason to actually limit this number to 30%. We've also made calculations for 40% and beyond, but I will explain later why we have been looking into the 30% scenario, as we believe this is the most realistic these days. DRI is made in a direct reduction plant, as we're all aware of, and most of the DRI these days is actually made in shaft furnaces, which could include, for example, annealed iron. And annealed iron technology could actually use either natural gas or coke oven gas or hydrogen, even syngas, and I would say any blend of those gases. For simplicity, we are actually ignoring the usage of syngas. So within the next few slides, we will only look into using either 100% natural gas or 100% coke oven gas or 100% hydrogen for simplicity. Usage of coke oven gas for the production of DRI is actually not new. And I would like to put those two examples to your attention. Those are two of the most recent industrial demonstration plants, which were commissioned and are currently operating in China to produce 0.5 million tons of DRI per year and 1 million tons of DRI per year using coke oven gas. So the usage of coke oven gas to produce DRI on its own, it is not new, but the industrial scale is emerging fast in China as we speak. Second to that, we know that high-grade ores are limited in availability. So ideally, our industry would be using lower-grade ores. Well, this is actually very attractive when charging this DRI in the blast furnace. So we have been looking actually into the usage of BF-grade pellets to produce a DRI with a lower iron content compared to an alternative scenario using DR-grade pellets, which would produce DRI with an iron content more than 90%. So this DRI is actually, I would say, sort of low-grade DRI. It has a moderate metallization, but it has a relatively high amount of gangue components. And we can charge this in the blast furnace because actually the blast furnace is the ideal smelter. And let us again look into the KPIs of the blast furnace when charging either DRI made by natural gas, or DRI made by coke oven gas, or DRI made by hydrogen. Again, you can see a coke rate reduction, which is similar for all three scenarios. We have reduced the coal injection rate somewhat. The reason actually being mainly the fact that we would then produce a little bit more coke. Also, we didn't want to violate the lower limit to the coke rate, which I already shared before. And the more coke we would actually charge, the more coke oven gas we could produce. And this actually balances out to the 30% I've already been mentioning before. So if more coke oven gas would be available to the industry, then the 30% that we have been assuming could be raised to 35, 40%, even beyond. But in reality, there's limits to the availability of coke oven gas. Again, if we look into the electricity balance, it's still a minor export when DRI is being charged made by using natural gas. We need to import electricity when the DRI is made by coke oven gas, because all of the excess blast furnace gas would actually be used for the direct reduction plant process gas heater. But the amount of electricity that we would need when using hydrogen is really very, very significant. If we would look into the scope 1 emissions, again, using natural gas has a benefit, but it is limited because of the CO2 emissions that are generated in the direct reduction plant when using natural gas, also when using natural gas for the process gas heater. A rather significant reduction could be accomplished when the DRI is made by coke oven gas, and the same is true when DRI is being made by using hydrogen. But if again we factor in the scope 2 emissions, then those would be quickly worse when DRI is being made by using hydrogen. and this DRI will then be charged into the blast furnace. So this graph actually suggests that the usage of DRI is beneficial, particularly when coke oven gas is being used to produce that DRI. Last but not least, we have a few minutes left. I would like to make a simple comparison to alternative top gas recycling technologies. I'm sure that most, if not all, of the attendees are aware of the basic configuration of top gas recycling. There's many different options which are being discussed and evaluated in our industry. This is just one example. It needs oxygen, which is made by an air separation unit, consuming electricity. It includes a process gas heater. It includes a CO2 scrubber. We've been assuming a VPSA. Excess CO2 is either emitted. We are not assuming CCUS. And the top gas would be recycled and injected also in the shaft to restore the heat balance. One of the main challenges actually in this industry is the scale up, because the scale up could have a dramatic impact in, the efficiency of the top gas recycling scenarios. And until top gas recycling is being demonstrated on industrial scale, we simply cannot reliably predict the efficiency of this technology. So we've been assuming, I would say, a moderate efficiency of top gas recycling as reported in the industry. And let's then compare again the KPIs of the blast furnace and the electricity balance. And what happens, this is actually sort of interesting, you can see right away that the coke rate of the one option using 30% DRI made by coke oven gas and the coke rate of the top gas recycling option, they were comparable, I would say. And in the electricity balance, it's also somewhat comparable. And again, we can make the chart. And as you can see, the CO2 emissions for scope 1 and scope 2 are also comparable. So we believe that charging the DRI using coke oven gas or top gas recycling oxygen blast furnace, they actually have similar impact on reducing CO2 emissions. But charging the DRI is already demonstrated on industrial scale. There's no new technologies, there's no scale-up risk, whilst those do exist for top gas recycling oxygen blast furnace. And this is the main reason why our current strategy focuses on charging the DRI, although we are not ignorant of the potential of top gas recycling oxygen blast furnace. Again, we can also compare the scope 1 and scope 2 emissions, and I would say that the two lines are somewhat comparable. I would like to end this presentation with some conclusions. We believe that realistic and effective technologies must be deployed right away, if not in the next 3, 4, 5 years. And those could include and should include application of best available technologies, maximizing efficiency, maximizing yield. Second to that, if gases would be injected into the blast furnace, ideally coke oven gas would be injected to reduce the CO2 emissions. Third, more significant emission reductions could be achieved by charging DRI made by using coke oven gas and also using the low-grade iron ores. And this altogether would actually rule out the need for hydrogen. There's no risks in scale-up. We can use low-grade iron ores, continue to produce high-grade steel in the basic oxygen furnaces. And this is why I believe that those are realistic solutions to reduce the emissions. Last but not least, I've just been sharing a few examples. In reality, we are already aware of the potential of raising metallics in the blast furnace to 40%, as demonstrated in Japan as we speak. We're also looking into maximizing metallics and converter steelmaking to 40%. And if we would add the one to the other, then an overall CO2 emissions reduction of 40% could be accomplished. And there are some other trick cards that we could add to actually reduce those emissions to less than 1,000. Thank you very much for your attention. If there would be any questions, I'm happy to answer.
Thank you, Ajay. That was an excellent presentation, and we have a couple of questions rolling in. Mr. Oliveira would want to know, in terms of CapEx and OpEx, what is the most effective option, DRI, coke oven gas, or top gas recycling?
This is a very good question. I can only actually give a very generic response. Any technology we've come to realize will raise the cost of crude steel. That is only feasible if either CO2 emissions would be penalized or if CO2 emissions reductions would be awarded by green steel premium. And it is not yet entirely clear to us which of those technologies would be the most economic. For sure, the investment into top gas recycling, oxygen blast furnace, and all of the auxiliary plants, it is somewhat comparable to investment into a new direct reduction plant, which is a mega number. And capital investment into any gas injection technologies, it is, I would say, rather moderate. I hope that answers the question for the moment.
Yeah, there is another question from Scott Norris. What is your opinion on the possibility of using biocarbon in the sintering and coke making steps to reduce the amount of coal utilized? These smaller quantity applications seem possible.
Again, an excellent question. First, let me start. There's a few more technologies that I could not share and present today because of time constraints. But usage of biocarbon in sinter making in itself is a very interesting technology. Instead, actually, we're working on another program to convert sinter making to pellet making, because pellet making CO2 emissions are much, much less than sinter making emissions. And pellet making could be much more easily electrified. So we're actually trying to sort of convert the industry to pellet making rather than trying to reduce sinter making emissions. But biocarbon could be used. We're actually also looking into the usage of biocarbon by means of pyrolysis. But our preliminary assessment, and this is actually one of the trick cards I could not explain, again, because of time constraint, we have already come to realize that injection of biocarbon is by far more simple and efficient than using bio coke or biocarbon in sinter making or blast furnace.
Okay, very good. One other question. What is the limit for using DRI in a blast furnace?
Well, as I already explained, Kobe Steel in Japan reported last year their industrial demonstration trials with more than 40% DRI. We also came across similar conclusions. You would need to alter some changes to the processes. So we believe hot DRI must be charged. Kobe Steel injected hot nitrogen. This is not a method. We believe a little bit more complicated. But interestingly, we also actually came to conclude already by our heat and mass balance model, ultimately, but not in the next 5 years, but ultimately, the blast furnace could be used as a smelter when being charged with 100% DRI. And then the coke rate could be reduced to less than 100 if it would be a nitrogen blast furnace instead of an oxygen blast furnace. And I would be happy to share those results in another AIST seminar in another few years.
Okay, thank you, RJ. One other quick question from Ashley Kruger. Where do you see CCUS in your planning?
Carbon capture and utilization and storage. We actually we are ignoring this for the moment entirely because we simply do not believe there's sufficient storage capacity available for the steelmaking industry. And usage of CO2 is not so easy either. Usually requires massive amounts of hydrogen. So we would actually be awaiting developments by utility suppliers to demonstrate the feasibility of carbon capture and utilization. But we have not been factoring in this option.
Okay. A last question from Anderson Morlato. Could you combine DRI, could you produce DRI from coke oven gas and also from recycled top gas from blast furnace?
That I need to check with my colleagues.
Okay, all right. Thank you very much. Let's all give a big hand to RJ for an excellent presentation, and I will hand it over to you, Joe. Take care.
Thank you. Thank you. You're most welcome.
Oh, that's great. Great presentation and great questions by the audience out there. I'd like to move to our next presenters here. We have David Osborne Dave Osborne has a Master of Engineering in Chemical Engineering from Imperial College in London. He graduated in 1990 and took a position as process engineer with David McKee in Stockton. Since then, he has undertaken various engineering, commissioning, sales, and R&D ironmaking roles around the world within the organization. He is currently the head of blast furnace technology in Prime Metals Technologies. After David, Gerald Wimmer is a PhD in mechanical engineering from Vienna University of Technology and an MBA. He graduated in 2009 and took a position as a simulation expert with Siemens VAI in Linz, Austria. Since then, he has undertaken various technology, engineering, and R&D roles around the world and within the organization. He is currently the Vice President of Converter Steelmaking at Prime Metals Technology with a focus on green transition. All right, we'll pass it over to Dave.
Thank you very much, Joe. Thanks everybody at AIST for organising this. Good, you should be seeing the full screen now. So, yeah, as I say, thanks to everybody. Gerald and I will be presenting on BF and BOF decarbonisation with an emphasis, obviously, on what can be done from a CO2 perspective, but also trying to give it an economic viewpoint as well without breaking any of the rules of sharing information that we're not allowed to share. We'll try our best not to repeat previous webinars, but I guess not surprisingly, there'll be some alignment with today's presentation from Reinud. So a bit of corroboration, perhaps. So I'm going to start the presentation. I'm going to talk about the blast furnace. I'll shift across to Gerald, and he'll talk about the BOF. And then we've got a summary slide at the end that I'll come back to. So slide 1 is remarkably similar to one of Reinud's previous Reinud's previous presentation. So I won't dwell on it, but just to re-emphasize that the blast furnace is the big emitter in the liquid steel route. And is therefore both a challenge and an opportunity in the short term. But preparing for this webinar, one of the questions that Joe Morey asked us was, what is a good blast furnace? And I had to think about that question and how to answer it. And for me, I guess some operators out there, some of you listening will be lucky enough to have very modern furnaces with a lot of the latest facilities and benefits that I'm going to talk about. But most people listening will probably have older existing assets and might be asking what I can do. So what I want to do is talk about not what is the best technologically available blast furnace, but what helps with OPEX and what helps with CO2. So what is a good blast furnace? And I just made a list of some of these items. But first, what does a blast furnace do? We have to be honest, the value add in the blast furnace is nothing like the downstream technologies. So what we're normally trying to do is produce the lowest cost hot metal for use downstream. And what lowers hot metal cost? Well, best raw materials, clearly. Can I have the finest coke? Can I have the world's best sinter? Can I have the best pellets, etc., etc.? But frequently, the best raw materials are either not a choice open to the blast furnace team, you're at the vagaries of the procurement team, or as we know, available quantities are coming down. So what we need to do is target the best operation with the raw materials available. So the next slide just talks about some of the technological activities which can be used to both reduce hot metal cost and CO2. And I won't go deeply on this slide. I've got another slide where I'll talk them through a little bit more, but it's not an exhaustive list, I'm absolutely sure. But these items, if utilized correctly, are all going to help reduce your OPEX. And I guess because such a large percentage of the cost of running a blast furnace is the fuel and the carbonaceous fuel, then most of these activities, in fact, on this case, all of these activities are going to bring the CO2 level down as well. So maintenance to maximize your availability and to minimize the time when the furnace isn't running efficiently. Bell-less top for burden distribution. Level 2 optimization system, blast temperature, maximizing your blast pressure, or should I say your top pressure, within your available constraints. Top gas energy recovery turbine, the TRT, if you've got enough pressure. Avoiding gas flaring, and the SIP oxygen pulsing, which I will explain briefly later on, which is a relatively new technology. There are a lot of other options out there for reducing CO2, but I wanted to try and discuss at a very high level, cost and benefit, because there are many options, more than I could fit onto one slide with photographs that you'd be able to read. So I've put a few just onto this slide. But what's important, I think, is then to talk about them individually and maybe try and rank them. And in trying to rank them, how do you do that? So I've put a series of technologies on the left-hand side here, and I'm going to, again, at a high level, try and rank them on OPEX, operational cost, CAPEX, that's the capital expenditure, CO2 benefit, and then some comments on the side. The one that seems to be most obvious from a cost benefit solution is the level 2 system, an optimizer for BF operations. OPEX, will it decrease OPEX? Of course it will, yes. What is the CAPEX for it? And you can see I've been very careful with how I've described CAPEX. I've called it very low. Everything else in my list is going to be either low or medium. I guess when you are looking at a particular plant and the cost of the modification, and I'm thinking not the cost that the OEM is going to sell you a technology, it's the project cost for implementing the technology, so what the steelmaker pays. So in my mind, low is in the region $1 to $10 million, and maybe medium is in the region $10 to $20 million. These are indicative. And level 2 is at the bottom end of low. So I'm going to call it very low. And depending on your starting point, of course, as we see a CO2 benefit of something like 2.5%. So that seems to me absolutely the no-brainer. Bell-less top BLT. Everyone has a BLT. Well, that's not everyone has a BLT, as I'm sure almost all of you know. And many people with a bell top operation have spent years and years optimizing the blast furnace operation with that equipment. But I still believe that a bellless top will give further control and further flexibility to help you reduce fuel rate and optimize the operation. So I have OPEX decreasing, CAPEX, as I say, to actually implement the BLT is probably low end of medium. And the CO2 benefit will be there. I would expect it to be there, but again, it will depend on the starting point, how good your operation is already. I'm continuing in the way I'm ordering these through starting with the OPEX in order to reduce hot metal cost. So I've put SIP next. This is the sequence impulse process oxygen pulsing. It's a relatively new technology. I've got a couple of slides on that. I didn't want to make this much of a promotional presentation, but I will explain that in case there are people out there who aren't aware of it. But this has been proven to decrease OPEX. The CAPEX sits again probably in the lower end of medium. The CO2 benefit is, all of these are incremental CO2 benefits, and some of them can be added together. But for this one, the payback can be very large, very fast on larger furnaces. So I'll talk about that later. Top gas recovery turbine and maybe dry gas cleaning. A TRT if you haven't got one, and if you have the top pressure to make it economic to drive one, which are both the proper questions to ask. If a TRT can reduce the OPEX, it's probably going to be in the medium range of CAPEX, and again an incremental CO2 benefit. Adding dry gas cleaning to an existing blast furnace, I guess, is going to push the CAPEX up even further to the top end of medium at the minimum, with a benefit to the TRT, but only if the TRT can take it. So maybe a small opportunity for that technology. For those probably few people out there who do flare all or part or most of their blast furnace gas, then the opportunity to install a blast furnace gas firing turbine exists. Again, a medium CAPEX, but something, if you are wasting blast furnace gas, then you're going to generate electricity. So again, probably a niche technology, but worth putting on the list. The benefits of hot blast temperature increase, I guess, are probably well known to most or all of you who are listening in, and there's all sorts of solutions to improve the hot blast temperature depending on your starting point and the age of your facility. So whether it's in the stove itself or whether it's by replacing your tuya stocks with energy-saving tuya stocks to give you that little bit extra blast furnace blast temperature. At the tuyas, there are a huge range of solutions which can be considered there. Which is why I've said that the CAPEX can vary from, I guess, virtually nothing from a quick study to tell you what you might be able to do, to relining an entire stove, if that makes sense. But if 100 degrees C, and apologies, I'm only working in Celsius in my world, so 100 degrees C hot blast reduces the fuel rate by, let's say, 10 kilograms. So there's a significant potential for hot blast temperature. Gas injection, so hydrogen-bearing gas injection, which could be natural gas or coke oven gas or hydrogen or some sort of synthetic gas. But we'll start with natural gas. Really depends where you are in the world. I guess if I'm talking to a lot of people based in the USA, then you've already got access to low-cost natural gas, and I don't need to explain the benefits to you. But coke oven gas, I would agree with the previous correspondent that you can get a better benefit from coke oven gas. I think the limits of availability of coke oven gas were well described 20 minutes ago. The only difference, I guess, is in the capex, because for coke oven gas you're going to have to install a compressor, which is going to be in the millions of dollars. And you're going to have to make sure that your coke oven gas is a suitable cleanliness in order to not clog up the system. But all of these things can be managed. I'm getting into now potentially the increase in OPEX. So, and again, of course, this depends on individual circumstances and access to raw materials, etc., etc. So it is very much a high level assessment. But HPI charging, probably you're going to have to buy in the HPI, so your cost of operation might increase. If you're not going to install an HPI plant yourself and you're just going to buy merchant HPI, then the capex is pretty low to be able to utilize and charge HPI. The references that were talked about just 10 minutes ago, particularly Kobe, I think if my memory is correct, they talked about up to 18% CO2 reduction. But it all depends on the availability and the cost of the HPI and the CO2 associated with the HPI. But large potential for HPI, I would say. Scrap charging, you're at the mercy of the scrap market, I guess. Scrap charging can be more expensive to implement compared to, for example, HPI charging. Particularly, I'm thinking of the preparation of scrap and whether you're going to make it easy to be transported on conveyor belts, or whether you can put it into a skip, which will be a little bit easier potentially. There are machines out there, I'm sure a lot of you will have seen, that can produce very nice looking balls of scrap which are easy to transport and charge, but all of that comes with a capital cost. Hydrogen, currently I would absolutely confirm that that's going to increase the OPEX of your plant. The capex in terms of, I would say, buying hydrogen over the fence, and that's why I put low. Certainly, if you're going to generate it yourself, then the capex is going to be back in the medium range at least. And many presentations, including one of the previous AIST webinars, talked about the limits of hydrogen injection at the TWIA predominantly, based on limits of the raft and the top gas temperature and the top gas hydrogen. I think, as was talked about just now, the challenges of low-cost green energy leading to low-cost hydrogen are a few more years away than everyone hoped when we started this CO2 discussion. And finally on my list, as I say, not an exclusive list, but on my list, biocarbon. Currently, my assessment of biocarbon is that it's expensive and it's not available in quantity, and it's variable and potentially variable in quality. It was demonstrated in Australia that you could blend some kind of biocarbons into your PCI injection system if that's what you've got. But I think the biocarbon market at the moment sees itself at some premium cost. And with the quantity that's being generated, perhaps that's not surprising. So I see hot metal OPEX increasing potentially with biocarbon, probably a small reduction in CO2 benefit as people learn to utilize it, blend it with PCI, for example. But it does sit at the bottom of my list at the moment. A very quick introduction to SIP technology, because This isn't meant to be a promotion, but just in case you weren't aware of it, and it's on my list of opportunities. So sequence impulse technology is an oxygen pulsing technology developed by ThyssenKrupp in Germany on their blast furnace number 1 at Schwelgen, Duisburg. And the oxygen pulse is used to clean out the back of the raceway, the bird's nest. Particularly, I guess, with PCI char, which is obviously a challenge for any furnace with PCI, but not a challenge for furnaces without PCI. But combusting, burning out the very small coke particles as well is what the technology can do. And by doing so, you're both extending the raceway and cleaning out the back of the raceway to allow gas further into the blast furnace. And one of the benefits that leads to is an ability to reduce your coke chimney size. And by reducing your coke chimney size, that means that your CO2 utilization can be increased, maybe by order of magnitude 1.5%. And that means that the furnace runs more efficiently. But the technology has also been proven to allow you to inject more PCI than you had been injecting, and by definition to reduce your coke rate by similar amounts. Picture of the plant at Schwelgen, and as you can see, the top of the picture there is a pulsing box for each tuya. What does it mean? This is what was seen at Schwelgen. As I said, ETA-CO, the efficiency of carbon utilization up, coke significantly down, coal up, fuel rate down, CO2 down. Again, an incremental CO2 reduction, but the coke saving, where coke is your most expensive fuel, can and does lead to return on investment of maybe 2 years for a project. And Primetals are currently building the first SIP plant outside of Germany in India on a 5,000 cubic meter blast furnace. So given all of those things, how do I move my blast furnace forward? And by my, I mean yours, because there's so much to assess. There's a lot of things you can do yourselves, and there's things where you might need help. This pretty picture is one that I took from a study that we did recently for one of our customers. It's specific to that part of the world, so ignore the values on it, but the columns align with the left-hand y-axis in terms of the fundamental costs, variable costs of operation and materials. And for various increases in PCI, addition of coke oven gas, natural gas, hydrogen, there are other graphs for many of the other technologies that I've talked about so far. Then the current OPEX change that particular customer would see is shown in the columns. So on the right hand side, it just again demonstrates that hydrogen is super expensive at the moment, and this customer's availability of natural gas wasn't particularly good. The circles are aligned with the right hand y-axis, and this is the CO2 level for that customer for the full scope 1 to 3. So you can then start to align the OPEX change with the CO2 change. And the bit that's missing then is the return on investment, which is where you're going to have to talk to technology suppliers, equipment suppliers, and take a view. But this for me is step one in determining which of those technologies might make sense for each of you out there operating an integrated steel plant. I'm now hopefully going to hand over to Gerald.
Yes, you can, Dave.
Tell me when to change the slides.
So we discussed about BF-BOF route. So we thought it's worth to spend also some time on the BOF route, on the BF step, the second step of this process. We have discussed a bit of metallics, how metallics input is changing the CO2 emission. And as we can see on the next slide, this is exactly the lever we have on the BOF converter. So on the BOF converter itself, we cannot do that much to reduce the CO2 emission. We need some carbon in the BF for heating, for metallurgical reasons, to remove the phosphorus, to purge out the nitrogen. But we have a lever by selecting the input material. And as you can see on the very right-hand side in this diagram, we see the typical materials that we can charge into the BOF converter, like hot metal, DI, and the related CO2 emissions. And we see, as we already discussed, hot metal production blast furnace needs a lot of energy, which is mainly carbon. That's why hot metal has a lot of CO2 produced, compared to the scrap on the very right, which has zero carbon per CO2 footprint per definition. So by varying the scrap mix in the BOF converter, we can reduce the overall CO2 emission by reducing the hot metal ratio. And that is shown in the diagram in the center. So here we have shown the CO2 emission of the root, blast furnace, and BOF converter total CO2 emissions as a function of the scrap rate. And we see, of course, that the emissions of the converter shown in green do not change, but the overall emission change as soon as we increase the scrap rate by about 1% of scrap rate increase, we get roughly a reduction of CO2 emissions by 1%. This will not lead us to carbon neutrality because the scrap rate in BOF converter steelmaking still is limited. But this is a nice, simple way for a first step to get to a lower CO2 emissions by increasing the scrap rate by some 5 to 10%. As we can see on the next slide, what are the main challenges to increase the scrap rate and converter steelmaking, as we're discussing mainly about existing plant is scrap logistics. So of course, we would like to do more scrap, means we have to purchase more scrap. So we need an inbound scrap logistics. We have the converter process where we have to ensure sufficient mixing and melting energy. And last but not least, scrap quality. So there is, of course, a topic with trace element in the scrap. If we do more on converter, we have to be careful that we keep the limits, for example, for copper and SN in our final steel. To melt more scrap, we need more energy. So we have to keep this energy balanced, what we take in and what we take out. And we can work on this energy balance by bringing additional energy, for example, by scrap preheating, by additional post-combustion, or simply by better process control to reduce energy losses, by better logistics, and by eliminating all the cooling agents that are still today used in converter steelmaking. And some examples of these tools to increase the energy supply and therefore the scrap rate we can see on the next slide. We can see some of these lenses here on the very right-hand side, the scrap preheating lens, where we can preheat the scrap before we charge the metal. Such system, for example, is used by voestalpine Donawitz. They have two small blast furnaces. When one of them is in relining or maintenance, they are short in hot metal and have excessive time on their converters. So that's a good trick to use this time for scrap preheating. If the scrap is hot, of course, it takes less energy for melting later during the process. And as a consequence, you can melt more scrap with the energy available in the hot metal. In the converter, we combust carbon, but not very efficiently. We just combust it to CO. That's why the converter off-gas, it has high calorific value and is collected and used in the gas holder. Another way to use the calorific value of this gas is to do post-combustion to CO2 already partly in the converter. This is happening in our process standard-wise to 10%. So if we increase the so-called post-combustion ratio to 20 or 30%, we can increase the scrap rate again by some 5%. And last but not least, of course, we have to minimize the energy losses. This is best done by having accurate logistics and accurate process control. And for this, it turned out that process models are very helpful. So the process model allows upfront to calculate the heat with the accurate energy balance. Then we know precisely how much energy is available and how much scrap we can process with this energy. And then we can order the right amount of scrap and charge the maximum scrap amount possible. All in all, these tools allow for a standard BOF converter to increase the scrap rates to some 25%. For higher scrap rate, we need better mixing, and this we can do with combined blowing inverter like KOBM, as is shown on the very left side picture. We're just doing a new project for KOBM for a customer in Korea. So this is a very special niche technology, but a nice one when it comes to metallurgy and to scrap rate. So for higher scrap rate, 30 to 35%, KOBM converter has an advantage thanks to its better mixing. And we see interest in this technology now for a green transition of the integrated route for maximizing the scrap rate. And now the combination, what we can achieve now, if we combine the reduced CO2 emissions per ton of metal and the higher scrap rate in the BOF converter, which Dave will show us on our last slide.
Well, this is the penultimate slide. Thanks, Gerald. So the final slide will demonstrate just in one picture what can be done today without excessive capex, without hopefully extending your OPEX, keeping you competitive. I've picked a blast furnace based on PCI. I've assumed that its normal situation, its current situation is 100% CO2 with a 10% scrap. There are things you can do to it to get down to 90% CO2 or 80% CO2, whether it's a PCI run furnace or a different fuel like natural gas. Other games are there, other tricks are there to bring the CO2 down from the blast furnace. And as Gerald says, in order to reduce the overall CO2 per ton of liquid steel down, then increasing the scrap rate is part of the solution. So I haven't tried to demonstrate the best available figures here. I've tried to make it believable, and that means that if you could get to 25% scrap, for example, you'd be able to do better than the 75% or 25% reduction through the integrated route. And that's the final slide. So thank you very much for listening, and question time.
That was great, guys. Thanks for the presentations. Those are really a nice little menu of things that you can do to kind of get things going today, which is helpful for everybody, I would think. I have a question from Andre Oliveira. He asks, he says, excellent presentation. Has a SIP condition with multiple injections been simulated? For instance, PCI natural gas or PCI and biocarbon? Thanks
for the question, Andre. It's something, let's say, we're working on at the moment. The benefits of PCI and gas injection, the benefits of SIP and gas injection will probably be a little less than if you're injecting PCI from, because you haven't got the char at the back of the bird's nest. But it is something that we need to model, and it is something that we're actively trying to understand, not only for the US market potentially, but for other people who might have access to lower cost gases. We've got a customer in India who already has access to a synthetic gas which looks very much like coke oven gas in its chemistry. PCI and biocarbon, no, we haven't tried to model that. But there are some interesting papers from Port Kembla, which if you get hold of me afterwards, they're publicly available, so I could point you in the direction of them as to how PCI and biocarbon has been actually tested. Let's see here. Another question from
from Andre, and this is a really kind of a general question around hydrogen. Even though it's expensive, the hydrogen route presents serious engineering challenges. I think a lot of the hydrogen that you kind of mentioned has just been on a test basis. But what's your feeling on the that type of engineering challenges if they're overcoming those, or now is it just a matter of paying the cost?
I guess long term, in terms of the engineering and what is effectively a piping and control system, then it's the long term effects on steel that perhaps are not well understood for us. As you say, Joe, we've been involved in trials of hydrogen injection into blast furnaces. Which means that we've designed systems suitable for hydrogen and not suitable for a small test, but in case they are utilized in the future to be valid in the future. And that is something to learn about, both from an engineering perspective and from an experience perspective. I guess the other thing about hydrogen, and one of the differences between a blast furnace and a DR shaft, is the gas utilization. And if you're going to put a lot of expensive fuel, currently expensive fuel, into the blast furnace, then you're going to get half of it back out again at the top. So you have to decide whether that is efficient use of your hydrogen. I've never thought that burning hydrogen for generating energy is the best use of hydrogen. So that it's those two things that I try and answer the question with, Joe. Long-term understanding of equipment and how to monitor it, make sure it's safe, and is it overall economic to use hydrogen?
That's great. Question for Gerald. Is the stretching scrap, is that actually something that's being done out there, or what are the prognosis of that type of practice out in the BOF steelmaking that's a modern practice, I guess?
So using scrapping converter steelmaking is nothing new, and plants being short in hot metal, especially during blast furnace relining, already have scratched their scrap rate to keep production as high as possible during that time. So the principal idea is not new. What's new now is to do this on a general base, not to produce more metal, but to reduce the CO2 emissions. We see a lot of plants having a look into it. So we see first Alpine doing the scrap reheating. We have done one project with an ArcelorMittal plant for the dual flow post-combustion, but still we are in the beginning. So I think at the moment, plants hoped to find easier solution for the green transition. So everyone was streaming for the one big step to have the topic done. Now it seems the fact that we are coming back to the small step, looking on the blast furnace, a lot of small ideas that in total end up at the big saving. Same, I think, is this BOF converter topic. So we see now interest coming back again, and we hope that we see more of this project going to be realized, just for the sake of our whole climate protection.
And here's a last question from Andre, and this is actually for all the presenters. For everyone, the path of maximizing metallization at the best balance point between CO2 emissions and cost per ton of finished steel converges on a strategic and short-term solution, despite being CapEx intensive, but one that gains special attention if it's produced near a steel mill. What are your thoughts on that?
I think we're all just trying to understand the question, Joe.
Yeah, so essentially, I think he's asking, you're balancing your CO2 emissions and your cost of, which is why we're all here, your cost of ton of finished steel. So you're thinking about building something that gets a high metallization near your steel mill, some DRI plant, I would imagine.
I guess I guess both Reinud and I have suggested that charging HBI into the blast furnace is a logical thing to do at the moment. I'll wait for Reinud to disagree because I don't want to be putting words into his mouth, that's for sure. But then it does depend on whether you want to stretch to building a facility next door or whether you can get, let's call it merchant HBI from a different source, and whether the market sees the opportunity to develop that that feedstock route. And I guess that I haven't seen that answered in public yet. Perhaps it's something people need to start thinking about. Perhaps Reinud has a better answer.
Well, we're actually looking into this because we are convinced that using DRI or to a lesser extent HBI is one of the most effective strategies. Question then remains, where should the DRI or the HBI be made? Well, if we're looking into a USA steelmaking plant, realistically and logically, that DRI would be made in the United States, as is already happening. If you would be looking instead into a European or a Southeast Asian steelmaking plant, you could consider merchant HBI made, for example, in the Gulf Coast countries. But our economic assessment, which we did not share, also suggests that you could and should consider on-site production of DRI using the coke oven gas, which would not be available in Gulf Coast countries. So there's sort of a trade-off, and in the end you need to weigh and forecast, I would say, energy prices and values in different regions. This is not straightforward, but I think time will tell.
Yeah. I want to again congratulate all the presenters for excellent presentations, and just want to highlight that the type of techniques that you are suggesting to reduce CO2 from existing facilities are not just reducing CO2 by 1 or 2%, but if I looked at the numbers that RJ and Dave presented, it could be as much as 25%. So that would be a significant advance. And along the same lines, one of the questions that came out from Juan Carlos Carpadron is that there are a lot of new blast furnaces that are being built in the world right now. China is replacing capacity, India is growing capacity, even places like Thailand, Malaysia, Indonesia are building blast furnaces. Do you see some of these technologies being incorporated in those blast furnace right at the design stage?
Yes, we do. For example, we are working on new greenfield blast furnace projects, particularly in India. And some of our more recent designs, we have already included engineering, I would say, allowances and construction allowances to implement the top gas recycling on the mid or the longer term. So we are already widening tower structure and other structural elements so that in time top gas recycling could be embedded. And again, time will tell if top gas recycling on its own is the most effective technology. But it would be sort of sad if you would build a new blast furnace right now and you cannot add those technologies later. Likewise, many of our more recent projects, we've also simple space allowances for piping and ducting for coke oven gas or hydrogen injection. Because in the end, and I'm sure that Dave will agree, it's all about space. The projects, many people believe that new blast furnaces are designed for 20 years. None of this is really true because the surrounding structures and utilities, as we are also seeing in the United States, they can last for 50, 60, 70, 80 years. And their spacing and dimensioning must be right to allow for alternative technologies sooner or later.
Dave?
I confirm that, Madhu. It's and I think we're involved in projects doing exactly what Reinu's just suggested, but also we've got, I guess we've all got the capability to look at the existing plants and to be innovative with the available space there as well. So just because you've got an old plant doesn't necessarily mean that these technologies can't be applied. And with 3D scanning and all the other technologies that we can do nowadays to make engineering more precise, it makes it a lot easier to find answers to these questions.
Yeah. One quick point I want to mention so it doesn't get lost. Found very interesting in Graal's presentation on BOF. He mentioned that you can tap steel at a lower temperature from BOF, and same thing applies to electric furnaces, but increase the temperature in ladle metallurgy furnace, and that's also a good way to reduce total CO2 if you have clean electricity being available in the plant. So thank you for bringing that point. We'll hand it back to Charlie, I guess.
I do want to thank all our presenters and moderators. It's been an excellent presentation. The AIST webinar series is both available in past webinars, each individual recording, or at this box, you'll have a curated list of now over 20 decarbonization webinars that are available one after another back to back. AIST also has a resource center with over 10,000 documents of technical interest in the steel industry. And there are in-person training that are planned for the first quarter of 2026, as well as the AIS Tech annual meeting, the largest annual steel event held in the country. Thank you all for your time. Thank you for attending. Thank you, moderators and presenters. We will close this webinar. Thank you all. Bye-bye.
Bye-bye.